Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, in today video session, we like to focus on learning outcome number 2 from our course information, which state that apply Maxwell equation to explain the transformation of field from static to time varying. So that should be our concern at this moment. So to talk about the transformation from the world of static field, which involve either electrostatic or magnetostatic, to the world of electromagnetic field. Okay, that should be our concern. And based on that issues, we have discussed about the transformation using this simple table. Yeah? So we have stated before there are 4 Maxwell equations, and from the 4 Maxwell equations that we discussed in the world of static field, we have been mentioned there will be 2 Maxwell equations need to be altered in the world of electromagnetic field. With that been mentioned, we have seen the first transformation based on the second Maxwell equation shown here, which is known as Faraday's law. Okay, we have done that. So logically now in this lecture, what we're going to do, we're going to talk about the second transformation, which is Maxwell equation number 3, and that is being summarized as displacement current density. Okay, that should be our overview about what we're going to discuss. So I'm going to put the title here. So we're going to talk about displacement current density. Okay, so to make it easy, so this particular current density is going to be represented with symbol J, because J is what we use to represent current density, and then you're going to see subscript D. So whenever we see subscript D being used for the J, that will represent our displacement current density. So for those who have textbook, you can open to sections 9.4, page number 439. Okay, that should be the topic, okay, in our textbook. So let's talk about this issue. So remember when we talk about Maxwell equation number 3, okay, so from our Maxwell equation number 3, okay, we call it static Maxwell equation number 3. So from which particular field? Magnetostatic. We state that the curl of H will be equal to J. And the J that we use at this particular stage is known as conduction current density. Okay? So we can see clearly it's totally different than what we intended to discuss here, which is known as displacement current density. So how actually we represent conduction current density equation? And if you refer to Ohm's law in point form, okay, the way we represent this conduction current density is using this equation. Remember? We derive this equation together when we talk about conductor material in the topic of electrostatic. And then we call this sigma symbol as conductivity. So we can see it's totally different than what we're going to discuss in this particular lecture. Okay, therefore that should be the one that we're going to relate to in our discussion. From where? From our previous lecture, so known as Maxwell Equation number 3, when we discuss about magnetostatic. Okay, so let's talk about this issue further. So what Maxwell did, he tested this equation in the world of electromagnetic. So now what's important here, we have to remember we are now currently in the world of electromagnetic. So no more in static field, because now we are in the electromagnetic field. So let's talk about this simple analogy experiment. So let's say you have a conductor, and the conductor going to be connected to a capacitor in series. So usually our capacitor will use dielectric material known as perfect dielectric. Okay, that should be the logical concept. What we meant by perfect dielectric, that the sigma will be equal to 0. Because we always stated dielectric material is an insulator. It will not allow conduction current to flow through it. So therefore, the sigma value must be equal to 0. Okay, so now we're going to test this experiment, this structure based on our Maxwell equation number 3. So this is what Maxwell did. Yeah? So in order to allow current to pass through the dielectric, we have to inject a current here. So the current here should be DC current or AC current in the world of electromagnetic. Because we remember the source of electromagnetic we discussed before should be moving charge with varying speed. Therefore, the current should be I depending on time. So we call it IT. Okay? So that should be the logical source we should inject in this model. Why? Because we are in the world of electromagnetic field. And we know that in electromagnetic field, the source must be charge moving with varying speed. So therefore, we're going to model the current flow here as IT. So we're going to have a current coming out from here, also I changing with T. Okay, so that should be the model. So what happened now, if I want to test this equation based on this model, so I have to adopt what we call it Ampere's circuit law. So using Ampere's circuit law. Okay, so we use Ampere's circuit law in this discussion. So what Ampere's circuit law said, H dot dl must be equal to I enclosed. Okay, so therefore, let's use that model now. Let's say I want to model it to be at this location. What should be the H here? Okay, using this model equation ACL. So what we need to do in order to relate this equation to this diagram, we must build what we call impedance loop. So now I'm going to build our impedance loop, okay, passing through H. Okay, so then the conductor actually penetrating through the area bounded by the loop. So the area that I'm going to define here as surface number 1. Okay, so let's do that model based on surface number 1 now. Surface 1 analysis. we're going to say that, okay, H dot dl going to be equal to I enclose J dot ds. Since we can see now a conductor passing through the area S1, so this conductor having sigma not equal to 0. Since sigma not equal to 0, so therefore current does exist, and this current is known as conduction current. So therefore this equation valid, meaning that Maxwell found that this equation can be used in this particular reference. Okay, so now, so what Maxwell did later on is quite interesting. So he changed the area of S1 now to be slightly different. What I mean by that, so let's say the loop still remain the same. Okay, the loop still remain as it is, but now we're going to state the surface is going to have this behavior. So it's a hole here. So now this is the second surface number 2. Okay, remember the loop still remain the same, the black line. So it's going to be empty here, but the surface going to be emulating this blue area, and we denote as S number 2. So let's analyze S number 2 model now. So okay, Maxwell did this. So he analyzed the same equation, Ampere's circuit law, but now referring to slightly different structure. The loop remain the same, but the area of interest going to be referring to surface number 2. Okay, let's refer to surface number 2. So what material that we use in the region of surface number 2? Okay, it's a perfect dielectric, correct? And then for perfect dielectric, the sigma must always be equal to 0, correct? So therefore, based on this equation, we can see clearly, okay, the H dot dl going to give you values. We agree? Because yes, the H still remain there. We're going to field exists in this particular point, because the field going to be generated. But yet, the mathematics based on the right-hand side, the J dot ds must be equal to 0. Agree? Because the sigma here is 0. Therefore, this equation is not appropriate for the second surface model analysis. Okay? So therefore, this is what made Maxwell feel a bit worried, because he found that this equation that been proposed, which is valid in the world of static field, will not be applicable in the world of electromagnetic field. Because why? This values not agreeable. On the left hand side you have values, yet on the right hand side is still equal to 0, because based on this model, when we use this equation, we cannot relate them together. So therefore this equation need to be modified. Okay, that's what Maxwell found. Okay, so that's what you can see. Good people, when they found something not correct, they will propose a solution to their sometimes when we comment about other people's work, we neglect to give the suggestion how to rectify the problem. So this what not happened to Maxwell. He found that based on the previous equation of ACL, Ampere's circuit law, this equation cannot be extended in the world of electromagnetic field, and now he are proposing how this lacking can be improved. So that's what we're going to discuss now. How to improve this in order to make it applicable in the world of electromagnetic field. So improvement. I'm going to talk about this issue now. Improvement. Okay, improvement of what? Maxwell equation number 3. So this is what Maxwell did. I'm explaining based on what Maxwell suggests need to be done here. Not me, yeah? I'm just referring to his idea now. So let's recall what we have seen before. So I'm going to put the idea now. Recall, okay, continuity current equation. Continuity current equation. Anyone can still remember what this equation looks like? We did discuss about this equation. Okay, so anyone can give idea what this should be appear? Good. Thank you for those who are answering correctly. Divergence of J equal to negative d rho v over dt. Okay, this is the process Maxwell used in order to improve the equation that he found not to be applicable in the world of electromagnetic field, yet can be used in the world of static field. So he started with using this very basic fundamental physics of current. So which is divergence of J equal to minus d rho v over dt, where we know the J here is known as current, and the rho v here we know as volume charge density. And we have shown the derivation of this model current when we talk about current in the world of electrostatic field. Okay, so what Maxwell did then, okay, this is what nice about Maxwell. He improved it by doing this process. So now, what he did, he substitute the J, okay, using the Maxwell equation number 3. What is it? Curl of H. Okay, so therefore the equation now becoming divergence, curl of H. Okay, that should be the thing that we need to do, just substitution, and other than that should remain as they are. Nothing need to be done. So that's done. So then what Maxwell did, he observed or he analyzed equation on the left hand side. So when he looked into this equation, what should be the solution to this equation? You have a del, you dot with the del, curl with the h. So del is a vector, h is a vector. So now let's think it in a simplistic way. If a vector cross with a vector, that cross product we're going to produce another vector, correct? The solution vector of that cross product going to be orthogonal to the first vector and the second vector. So meaning the product of the cross product here will be orthogonal. So when you have that vector, you dot with the original vector of your cross product, the solution must be equal to, yes, 0. That should be the solution of the triple product. So meaning that when you do this mathematics, the solution of this vector product will end to become 0. But yet, based on this equation, on the right hand side is not equal to 0. So Maxwell found that there is something wrong, because based on the substitution of the equation that he used, he found the substitution will end with 0 solution, yet the original solution is not equal to 0. So now he have to make it correct. So what you think that Maxwell did in order to rectify this error? Good. So Maxwell add this term, d rho v over dt. So this is what Maxwell did. Okay, he just add this term so that the final solution should also agree with the left hand side term which is equal to 0. So this one, that additional term. Okay, so then what you have now, something that have been corrected. So can we go further now to talk about whether this additional correction can be rectified? The issue that he found initially based on the surface number 2 model. So let's do that investigation together. Yeah? Okay, so let's do that by going back to the equation. I'm going to rewrite the equation on this particular space so that going to be easy for you to observe. Okay, so what we have n just now. So this should be curl of h should be equal to negative d rho v over dt plus d rho v over dt. Okay, now, based on our previous model, so this particular term, we can substitute with what's known as divergence of J. Agreed? That's we known as continuity current equation model. Then what he did later on, he going to substitute this rho v with Maxwell equation number 1. Divergence of D will be equal to rho v. Okay, so what he end up on the right hand side should be equal to divergence of J plus divergence of dd over dt. So now, just by focusing on the term of this blue box on the left hand side, what Maxwell conclude that the curl of H will be equal to the J plus dd over dt. Okay, that's what he conclude. And the J that represented here is known as conduction current density, which is still agreeable with the original Maxwell equation in the static field. But now the additional term now he denoted as what the title of our discussion here, known as displacement current density. Okay, so there you are. So let's talk about this issue going back to our original capacitor. So now let's recall that. So you have now a conductor carrying I changing with time. So there you have a surface of the upper capacitor and the surface of the lower capacitor and another conductor. So what actually being carried by the current is a charge. So what we're going to denote that when the current flow towards this surface is going to contribute surface charge. And the surface charge also will be depending on time. Okay, so what's going to be produced when you have a surface charge? You're going to produce what is known as electric field. Okay, the electric field also be depending on time as well. So now you can see based on this equation, okay, when you have electric field changing with time, this term will not be equal to 0. So therefore what we're going to see now, they're going to be a current flow, and the current flow here is known as displacement current. Okay, so when you refer that to our original model here, because now there's a current flow, but it's not the conduction current that we referred earlier, but now we know the current is known as displacement current. So therefore, this term now will not be equal to 0. You're going to have values. Okay, so therefore Maxwell rectified this small error by do some investigation by adding certain term, and from the additional term he defined that additional term as the new current that appear in the dielectric material, and the current will be based on the electric field. And now you can imagine how the information actually been transferred from your handphone to other destination through the medium of air, and we know air actually is a dielectric material, by utilizing electric field changing with time. So that actually known as displacement current. So now what you can see, a complete cycle of the continuity is complete in circuit theory. Okay, the current flow here known as conduction current. The current flow here is known as displacement current. So when you arrive at the conductor material, it's converted back into conduction current. So you can see a continuity is happening, which is not been seen before. Before we just use formula to actually discuss about this continuity. Okay, so therefore hopefully from this simple discussion open your view regarding the fundamental of electrical world, that show you how the current actually change themselves to make it applicable to the environment where the current is actually flowing. So therefore that should be our first objective, talking about displacement current. So I'm going to talk about what is very common in our world. We call it to be lossy capacitor. Okay, so we're going to talk something that very common in the world of engineering, lossy capacitor. Okay, let's discuss about the capacitor we talk in electrostatic. So in electrostatic, we have a capacitor, correct? So let's say we take the most simplest model of capacitor, the parallel plate capacitor. So you have a conductor, and then going to be isolated by dielectric, and we call this dielectric as perfect dielectric. Okay, where perfect dielectric being represented by sigma always equal to 0, and we're going to define the permittivity as epsilon, as what we've seen before. Yeah, so that should be the model before, and now we just learn about dielectric can be that exists in the real world is not perfect, because perfect dielectric is very expensive. Yeah, because it's like a perfect gold, expensive material. So now what we have to work with in order to produce devices, we have a cheaper material. Okay, so with that, what we're going to draw now, another capacitor. So the capacitor here, we're going to use what is known as lossy dielectric. And as we know, capacitor to store energy, and the simplest reference that we can relate this is our handphone battery. And most of you agree, when you charge your handphone battery, even though you're not using that battery, after a certain time you can see the power stored in that battery is being reduced. So that is due to why? Due to the material that they use to fabricate the battery based on lossy dielectric in order to produce something cheap. So if they use the perfect dielectric, it's going to be very expensive. So therefore, for lossy dielectric, the most important difference, the sigma here not equal to 0. I'm going to define now the permittivity as epsilon prime, just to show the difference between these two together. Okay, so what happened when the current flow into this lossy dielectric? Okay, so now we're going to model that. So when the current flow I, T, So now we have the second equation known as Maxwell equation number 3, state that the curl of H equal to JC plus JD, correct? This is what we just proved together. So now what we can see by this simple analogy, the current going into is total current I. So when it's entered the capacitor, it's going to be split into two. So it's going to go to the left. I'm going to denote that as IC. Why? Because it's known as conduction current. And we can see from this term, it's going to also produce what is known as ID. Okay? So based on this simple mathematics, the current can be split into two, conduction current and displacement current. So now, in order to make it clear, I'm going to add extra information, the lump element. So the element that's going to represent conduction current would be known as resistor, whereby the element that we use to represent our displacement current would be known as capacitor. Okay, that should be our equivalent circuit of a lossy dielectric. The current now going to be split into two, IC, conduction current, ID, displacement current, and the component that we associate with those current will be resistor as well as capacitor. Resistance going to be assumed as loss component, and IC going to be known as stored energy. Okay, so therefore for us in capacitor designer, there are going to be a parasitic effects whereby the C is going to be what we want it to be, want to store the energy. So the engineer have to think about how to improvise in order the resistance to be reduced or eliminated. And then we can relate this R based on our previous discussion when you talk about electrostatic, which is negative E dot dl divided with what? Sigma E dot ds. Remember? The field theory method, and our capacitance we can determine using the integrations of epsilon E dot ds divided with minus E dot dl. Yeah? That's how you actually use model that we discussed before in order to calculate the specific value of the capacitance. Yeah? So it's depending on the E as well as the material. So now the material here should be epsilon prime, remember? So it should be epsilon prime. So that should be equivalent circuit of a lossy dielectric, because in final exam, I presume this is what going to be a popular question need to be always been asked before. Yeah? So that should be what we're going to be seeing. When you use a lossy dielectric in a capacitor, we're going to produce two component, and how we develop this component based on our Maxwell equation we developed earlier. So the conduction current and the displacement current, and then we utilize what we have learned before in the static world to determine the resistance and the capacitance, and then you can determine how much energy lost, how much energy stored in the lossy capacitor. Okay, that should be the first thing that we should observe. And then the second thing that we're going to discuss here, remember, we always talk about dielectric material a lot in the world of electrostatic. And then, so in the perfect dielectric, we always said that D equal to what? D equal to epsilon E, remember? So that should be the model we used, okay, to talk about electric field density, electric field intensity. The relationship between these two electric field components were based on the permittivity. So this is being discussed in the world of perfect dielectric. So what happened of this equation when we venture into lossy material? So what happened to this equation? D, is it equal to epsilon E again? Because now the material is slightly different. It's no more perfect. Okay, so do we need to relearn something totally new, or we can use the original equation but just need to modify that equation in order to make it usable for the lossy medium? So what you recommend then? Good. We should use the original equation and just need to modify that equation in order to make it applicable in our new dielectric type. So how we do it? Okay, the question, how that we able to use original equation in the perfect dielectric, and yet that equation can be used in the case of lossy dielectric. So in order to do that, so let's say we do this comparison. Okay, on the left hand side here, based on perfect dielectric, and the space on the right hand side here based on lossy dielectric. And for perfect dielectric, we know that the sigma is equal to 0, remember? And epsilon, whereby for lossy dielectric, the sigma not equal to 0, and then permitted epsilon prime. So that should be our basic parameter regarding both dielectric mediums. Okay, so now, what I'm going to do now, I'm going to use this equation again. What equation is this? Okay, this equation. Okay, that's what we're going to use again. Okay, in order to use the equations, so okay, electric field. Okay, let's talk about this issue. Assume to be what? Assume to be sinusoidal, correct? Magnetic field also we always assume to be sinusoidal. Okay, sinusoidal is the important term here. So actually, how we represent sinusoidal wave? Good. So meaning that the E, I can denote it to be E naught exponential j omega t. Correct? Because we always model our wave to be sinusoidal. So when you see the term sinusoidal, you can represent that particular parameter with this exponential j omega t. And by using Euler model, this is actually known as E naught cos omega t plus j sine omega t. Agreed? Okay, so that should be our first thing that need to be clarified, because when we model electric field, always to be sinusoidal. When we model magnetic field, also going to be sinusoidal. So when you have the term sinusoidal, that condition can be represented mathematically using the exponential j omega t. Why? Because that actually having the term of sinusoidal, the cos term as well as the sine term, as shown by these equations. Yeah? So now, if I'm saying to myself now, d E over dt mathematically going to be equal to what here? So let's do this differentiation. Then you're going to say to me, doctor, you're going to be equal to j omega E naught exponential j omega t. Agree? So now, if I rearrange the equation so that it's going to be known as j omega E, is it correct? Yes, and then we can see simple deduction here. Whenever you see this term d over dt, we can replace that term with j omega. Okay, so that's the idea that we're going to utilize in this discussion now. Okay, so let's recall our Maxwell equation. So for the first one, I'm going to say based on perfect dielectric, the curl of H here will be equal to 1. Okay, remember JC, sigma E, dd over dt, yes. There's no sigma, going to be j omega epsilon E. Do we agree? Good. And for the lossy, it's going to be the curl of H now, going to be equal to sigma E plus j omega epsilon prime E. Because lossy, the sigma value is not equal to 0. So now, when we compare these two together, okay, so I'm going to say now, j omega E going to be equal to sigma plus j omega epsilon prime. Okay, can we see that logic now? And so, what we can conclude now, the epsilon actually equal to epsilon prime 1 minus j sigma over omega epsilon prime. That should be the equation that we can see coming from these relationships. So what happened to our original equation that we derived for the world of a static field? Perfect dielectric can still be used in the world of lossy dielectric by denoting now in lossy dielectric the D going to be equal to epsilon prime 1 minus j sigma over omega epsilon prime multiply with E. So that is the thing that we need to do in order to use whatever equation that we derive in the world of electrostatic based on perfect dielectric to be used in the world of electromagnetic based on lossy dielectric by converting the epsilon to be in the complex term. Okay, that should be very important. Okay, extending further, when you see this equation, this term that we can observe here is very critical in the world of engineering, especially electrical world, and this term is known as loss tangent of the material, tangent. Yeah. So loss tangent, so whenever we talk about material in future, this term is very, very important. I'm going to explain later on. So loss tangent actually sigma over omega epsilon. If you look further, actually you can define as the conduction current divided to the displacement current. Okay, that's how you determine the loss tangent value of given material by dividing, taking the ratio of conduction current density to displacement current density, or in term known as sigma over omega epsilon prime, yeah, because we are talking about lossy dielectric. So let's talk about that further. So what is meant by loss tangent? Okay, I'm going to discuss, this is going to be my last topic of this video, loss tangent. Okay, so in circuit theory, yeah, you just put the word circuit theory. So how we categorize material? Okay, material. So we have very simple conductor. What else? Let's say two main component and dielectric. So we're going to ignore the other term, dielectric. So how actually you define conductor and dielectric in the world of circuit theory? By looking at the value of sigma, conductivity. Okay, so for conductor, we know the sigma will be equal to, not equal to 0, whereby for dielectric, we're going to denote sigma will be equal to 0. So that's very simplistic way of categorizing material in the world of circuit theory, or in electronic, or in power system. So, but now in electromagnetic field, the way we categorize material is more critical. It's very simple analogy. Yeah? So let's talk about seawater. Seawater. Okay? So whenever I look into seawater, same seawater, So let's say I'm generating a signal now. So frequency very high. Okay, for example, 5G. So what should be the frequency range for 5G communication system? Yes, let's say make it to be 2 gigahertz. Actually, it can be vary, so let's assume it to be 2 gigahertz. So the seawater at this frequency is going to behave as what? So is it going to behave a conductor? Or is it going to behave a dielectric? Okay? So at high frequency, seawater going to behave as dielectric. Meaning that you cannot use high frequency transmission wave to communicate under the seawater because it won't propagate very, very far. Okay, with this particular frequency, the most distance that the signal can propagate is only in millimeter range. Okay, but yet when the frequency is very low, the same seawater now acting as conductor. Proof. Whale. In bahasa Melayu, ikan paus. How actually the whale communicate to each other? Okay, if the whale on the North Pole want to talk to the group of whales in the South Pole, they use sound, and the sound actually based on very, very low frequency. Okay, and you can see now the wave can propagate through the seawater without any problem. So, because the seawater at that low frequency is behaving as a good conductor. So now, in the world of electromagnetic, to categorize a medium, so you have a medium now. So first important, the parameter of the medium, which is the epsilon, what else? The sigma and the mu going to be critical. Okay, that's going to be important in defining what medium that we are dealing. And the second important information that we need to gather is actually the frequency of the signal of our design. We want to design for communication purpose, we need to know what frequency we are dealing, because that's why when you talk about high frequency design in the world of electronic, computer, so frequency play a very important role in the actual design, because the frequency is going to affect the behavior of the used material in that design. Okay, because that's what we discussed before. The same seawater, frequency very high, is acting as dielectric. It won't allow the signal to pass through it easily. Yet the same seawater, when you use low frequency, will allow the signal to flow through it without any problem. So therefore, in real high frequency design, we cannot use the simple way of deriving material. So what we have to use now, okay, material now need to be defined based on loss tangent. Okay, that should be the properties the engineer used in order to categorize medium at high frequency applications. Loss tangent, what is it? Sigma over omega epsilon. So now, what we're going to see now for us, based on the loss tangent, we're going to have good conductor, bad conductor, perfect dielectric, and lossy dielectric. See, we're going to categorize more detail. So very important in the world of designing, yeah? Because remember, the thing that you're going to produce need to be buy by people. So you want to sell something that optimum yet to be cheap, and the cost always affected by the material that you use in your design. Yeah? So for good conductor, loss tangent sigma over omega epsilon very high. Okay, that's how the engineer always show very high. The numerical value depending on which company you are working. Okay, and for bad conductor, loss tangent low, perfect dielectric loss tangent equal to 0, and then lossy dielectric loss tangent going to be not equal to 0, but it's very small. Yeah, so very small. So if the loss tangent becoming high, it's going to be becoming bad conductor. So therefore you have to see that. So the actual numerical value depending on the reference that you use, the standard that you use. Is it IEEE standard? Is it other standards? So different countries try to propose their own standard, because by actually controlling the standard, they are actually dominating the engineering environment in the real world. Yeah? So that's what you have to see. Okay, so that should be very important parameter, the loss tangent. So inshallah, I'm going to discuss example in my coming video known as tutorial video. Hope my simple explanation here, sorry about the length that I used to discuss about this more practical thing, but inshallah it's going to be beneficial for us, all of us. So with that, I'd like to say thank you very much. Inshallah, we're going to see each other again in my coming video. Assalamu alaikum wa rahmatullahi wa barakatuh.